Hello statistics student, this video is for chapter 3.3, 3.4. Compound events, especially events that involve multiple steps such as sampling. When we sample one and then the second one and the third one. So we are interested what is the probability of sampling certain outcome but with replacement versus without replacement. And we say if it is with replacement, we can use the independent multiplication rule, which is just probability of A times probability of B times probability of C. Just keep on multiplying. You don't have to look at how to do conditional probability, right? So it's very simple. So as much as possible, we want to use the independent rule. Just keep on multiplying because dependent is harder. I didn't do any dependent example because usually we don't, because it's very complex. So how do we actually treat? But in sampling, we actually usually we do without replacement because we actually want like 10 different subjects. All the subjects are different, so you can interview them, right? So how can I treat sampling without replacement as independent? So it is possible if one of the following is satisfied. Assume that it's a very big population. When the population size is not given, you don't even know how many you are sampling from. It's just, like in the last example, we have 300 adults that we are sampling from. The population size is 300. And then we just picked from them, so you know what is probability of A. But in this particular case, only probability of A is given, or the relative frequency of a category is given. So in those cases when it is, by itself, you know that, they are sampling from all adults in the US, then you know that the population is really large. So even if they are not replacing one adult, there's so many adults you can choose from. It is really rare to pick two at the same time. So we can assume that it is as if it's the same as without replacement. Okay, you would have, even if you don't replace them, you would have all different ones. The second is you use a 5% guideline for composite calculations. So if your sample size is 5% or less, no more than 5% of the size of the population, you can treat the sampling as independent. And actually, this is almost the same as in B when you have a really big population and you're only picking like 300 adults or 300 student even in a college. Those are less than 5% of your population. In those cases, even if you are sampling without replacement, you are not going to do. It is very low chance of getting the same students or the same sample. So you would just treat them as if they are sampling without replacement and treat them as independents. So let's do an example. The example would be, suppose 10% of adults in the United States use drugs. Find a probability of 3 selected adults who use drugs. So in 3.3, 3.4, we're always looking at probability of selecting multiples, right? So they have this category. The category is they use drugs. And so because we don't even know how many adults we're talking about, they say all 10% would use drugs. So if you're selecting one, the probability of 1% use drug is just that percentage. Probability of 1 use drugs is 0.1. And because the samples, the adults, in the United States is so big, we can assume that the sampling, although it could be without replacement, but we would assume the sampling are independent. We'll just keep on multiplying to do. And if we want to find all 3 uses drugs, so we'll say drugs, and then the second is drug, the third also use drugs. Just keep on multiplying without thinking, I pick one, so I have less to choose from. There's no less to choose from because this 10% is in general for the whole population. So you just multiply the 3, so that this would be the chance of having all 3 of them use this drug is 0.001. Okay, so this is when you do not have the sample size, and then you just assume that it is less than 5%. The second example, example 2, is you do have a sample, you do have a population, and you're picking from this batch. This batch is your sample. You're selecting some, you're selecting 12. So this would be your sample. But the 6,400 is your population because you're picking from that, right? And then we are talking about a category. The category are defective. Defective category is 80. The 80 out of 6,400. So population size 6,400. Sample size is 12 because you're sampling. You are selected. So you're not selecting 80. 80 is the category. So we want to find probability all are good. All 12s are good. So the first is good, the second is good. So this is the same as we're doing sampling by independent. Can I do it by independent formula? So it would be 12 over the sampling proportion is, I'm going to just check if I am just sampling very little. So look at 12 over 6,400 is 0.00188. So this is less than 5%, right? Less than 0.05 because 0.001 is less than 0.005. 0.05. So if we're just picking very little from 6,400 light bulbs, so we can we're assuming as independent by applying this 5% rule. So what we can do is all 12s are good would be the first is good. So you have to look at how you can get one good and also one defective. So one good is how many are good? So 6,400 minus 80 is 0.9875 divided by the total. What is the probability of you select one? So this is like last time. One that is defective is 80 over 6,400. And that is this number. So it's still just one. Now we move on to 12. Okay. To do 12, it is 12 steps, right? The probability the first is good. The second is good. You see how you are going to multiply them. So it's not adding, it's multiplying. So you would do the first is good, the second is good, all the way the 12 is also good. Because that is how you make all 12 are good. So you would keep on multiplying 0.9875, 12 times. Okay. And so you will use decimal to do. We would use exponent to do. And you put in the calculator. In a calculator to do exponent, you do 9875 up arrow 12. Okay. And in decimal, the way you do it would be you go to the decimal calculator. If you don't have your scientific calculator, you can get this calculator up, and then you would say, okay, 0.9875. Do the A to B, and it would go up, right? 12 times. Equal. Oh, you don't have to say equal. So that's the answer. 1 to 3 places, 0.859, and then add 1.860. 0.860. So that's how you do. At least one, we talk about what is at least one. At least one of something is 1 minus probability of all good. All of them are good. So if all of them are good, that would be the opposite of at least one is defective. So what is probability of all good? All 12 are good. We already calculated 0.860. So it's 1 minus 0.860. So that is 1 minus 0.860 is like 14, right? 0.140. Okay, at least one defective out of the 12. You're not picking one, you're picking 12. But at least one out of the 12 is defective is 14%. So this is how you do all good, all defective. All defective would be very low. You can see that I didn't do all defective. If you are to do all defective, that means the first is defective. All of them are defective. So it will be 0.0125. Use this, right? 0.0125. Or actually, you should use the fraction. And then 12 times. you can tell that this is really small number, 0.0, 1, 2, 5, and then 12 times. It would be like, yeah, really small, 0.000. So if you run 3 Hamilton's place, there's no chance that you can pick all 12 are defective. So remember, you're picking 12. Sample size is 12, so that's the chance. Then we have a last portion, which is rare event rule. So which is from the Triola book. It's not from the OpenStax book, but this is a very important concept. The main reason why we're doing probability is actually understand the rare, be able to apply the rare event rule. So we'll use this in the next video. We'll go over this in the next video.